In this presentation, we will explore the essentials of electrostatics as it pertains to the radiographer. A firm grasp of electrostatic principles are essential in understanding many of the phenomena observed in radiography, electromagnetics, and radioactivity. For the term electrostatic, the root word electro refers to electrons, and the modifier static refers to not moving. So, the whole term refers to a study of stationary electrons, but you will find that electrons don't stay stationary for long. They tend to move about for a number of reasons. To begin, what is an electron? Electrons are often described as fundamental, small, negatively charged particles, and electrons do exhibit particle properties. For the sake of simplicity in this presentation, I will characterize electrons in this form. In modern physics and chemistry, electrons also exhibit wave characteristics. Electrons don't exactly orbit around a nucleus in circular orbits, but rather as three-dimensional probability clouds. If this sounds complicated, it is, and explains my reason for characterizing electrons as particles. Actually, electrons display both particle and wave properties, and their true nature is not well understood. In the world of electrostatics, items can have a positive or a negative charge. Positive charges arise from the presence of protons. Materials exhibiting a positive charge will have more protons than electrons. Basically, some of the electrons have been removed. If a free proton exists, it will quickly combine with an electron and become a hydrogen atom, with protons forming its nucleus. Protons only exist in the nucleus of atoms. They do not exist in a free state. Since the nucleus is part of the atom that forms the material holding the positive charge, protons don't per se flow. When electrons flow from one point to another, the positive charge will virtually flow in the opposite direction. To keep things simple, when charges move, I'll refer to electron flow rather than positive charge flow for this lesson. Negative charges are associated with electrons. Electrons exist in orbitals surrounding the nucleus of the atom, and for some materials can be easily removed or wiped off a material's surface. Additionally, electrons may also exist outside of the atom itself, occupying spaces between the atoms. Atoms with more electrons than protons have a negative charge and are called ions, an ion being a charged particle with either a positive or negative charge. Here are a couple additional facts that are vital in understanding the behavior of static electric charges. All charged materials have an electrical field surrounding them. This field exists regardless of whether the charge is positive or negative. The existence of the field means that the charged particles or objects can interact without touching or coming into contact. The first law of electrostatics states that like charges repel and unlike charges attract. Particles with the same charge will repel. Two positively or negatively charged particles will repel each other. Here we have a negatively charged pool ball on the left and an electron on the right. The electron is propelled at the pool ball. As the electron moves closer to the pool ball, the force of repulsion grows until the electron is diverted from its path and misses the pool ball. Objects with opposite charges will attract one another. For either repulsion or attraction to occur, the two particles do not need to touch. They just need to be near one another. Here we have a positively charged pool ball on the left and an electron on the right. The electron is propelled near the pool ball. The electron is initially propelled along a straight line past the pool ball. As it moves closer to the pool ball, the force of attraction increases until the electron is diverted from its path and literally hits the pool ball. The electron will go on to join with a charged atom and negate its charge. The second law of electrostatics may appear familiar. It is the inverse square law applied to electrostatic force. Specifically, the second law states the force between two charged particles is inversely proportional to the distance squared. What is most important to understand is that two charged particles, as they become closer together, the force of attraction or repulsion will increase exponentially. Here we have two electrons repelling one another. The force of repulsion is determined by the inverse square law. Now we take two electrons at 1/2 the distance from the previous pair. They will repel each other with 4 times the force. Since the inverse square law is involved, it is possible that your ability to do the math may be tested. Hopefully, this equation looks familiar. The biggest difference is that the force replaces radiation intensity in the formula. Substitute the numbers for the variables. Solve for x. Do the math, and the distance increases by 1/2. The force between the charged particles increases by 4 times. The study of electrostatics has a very old history, dating back to before the 17th century. Back then it was known that electrification would occur by rubbing two dissimilar non-conducting materials together, like a glass rod and wool. For materials like glass, electrons can be rubbed off their surface, leaving a negative charge on the wool and a positive charge on the glass rod. It was soon discovered that touching a charged object to an uncharged object would cause a charge to migrate onto the uncharged item. This was known as electrification by conduction. After conduction was observed, it was also discovered that bringing a charged object near an uncharged object would cause the uncharged object to display a charge. This was called electrification by induction. This is due to the electrostatic field that exists around a charged object and the fact that charged objects can repel or attract one another without coming into contact. Additionally, it was found that static charges tend to collect or concentrate around particular shapes. The brown shape below is an example of a shape with two distinct curvatures. The top and bottom of this particular shape display a gentle curvature, while the ends have a sharper or higher curvature. In the case of this object, charges will concentrate or are attracted to the ends, where the curvature is greatest, and the charge is more spread out on the top and bottom, where the curvature is less. To summarize, sharper or tall pointed surfaces are attractive to static charges, and charges will concentrate or be attracted to these surfaces, while rounded surfaces are less attractive to charges and are more appropriate for storing or collecting a charge. Finally, there is the concept of ground. For an object to be grounded, it is literally connected to the earth by a wire or a conductor driven into the ground. The earth is considered to be an infinite reservoir of electrons and can accept or provide electrons as needed. If you have excess electrons to get rid of, send them into ground. If you have an excess of positive charges, The Earth can supply electrons to negate the positive charges. Connecting a charged item, whether negatively or positively charged to ground, will discharge it. The symbol on the left is one used to denote a connection to the ground. Here is the picture of the electrical service box in my basement. This tan metal box contains all the circuit breakers protecting the electrical circuits in my house. Coming out of the bottom is a copper wire that grounds the breaker box to the earth. This connection provides a pathway to ground for any electricity that might come in contact with the metal box enclosing the electrical service. Notice that the wire is connected to the top of a long copper post driven into the ground. All home electrical boxes have this as a safety measure to prevent electrocution. It can also offer some protection in the event of a lightning strike to your electrical system. Here is an example of a very attractive object, a cell phone tower. A tall pointed structure, it is very attractive to lightning. The picture on the left is its base. Note the ground wire attached to its base. This wire provides a path to ground and protects the tower if it is struck by a bolt of lightning. The scar on the side of this tree was caused by a lightning strike. Tall pointed structures that are grounded are more attractive to lightning strikes. The tree is connected to ground, and the water in the tree provided a conductor for electrons to flow to ground. This object represents a Van de Graaff generator. In the early days of radiography, Van de Graaff generators were one of the means scientists used to generate the high voltages necessary to produce X-rays. This particular generator will collect electrons on its spherical surface. The electrons will collect on the surface of the ball because they repel one another, and as the electrons collect, they will seek a position that is as far as possible from one another. I will illustrate the charges collecting as electrons on the surface of this metal ball accumulate. When the first electron is deposited on the ball, it can go anywhere, so I'll arbitrarily place it here on the left side of the ball. When the second electron appears, the electrons repel one another so that the second electron takes a position 180 degrees first on the surface of the ball. This position provides the greatest separation as possible since the electrons repel one another. When a third electron is added, the electrons redistribute. They are now separated by 120 degrees and as a result are closer together and repelling each other with more force. A fourth electron again redistributes the electrons' positions so that they are separated by 90 degrees on the surface of the ball. Also note that the distance between the individual electrons has decreased as more collect. Moving from 2 to 4 electrons cuts the distance between them by about 1/2 the distance, or that the force of repulsion between them increases by a factor of 4 times, due to the second law of electrostatics. Again, charges collect on the surface of an object in an effort to be as spread out as possible. The more charges collect on the metal ball, the distance between them becomes smaller and smaller, and the more the force of a repulsion increases. Here we have 2 metal balls. The ball on the right is charged and the one on the left is connected to ground. The charges on the right ball collect and don't flow to ground because there is a gap between the balls, and the force on the charges isn't sufficient to enable them to jump the gap. As the charges are added to the rightmost ball, the force of repulsion increases and continues to build until a spark jumps from one ball to the other. The charges continue to flow as a spark to ground until their concentration on the right side ball falls below the threshold of spark creation, at which point the spark stops. This production of electrical force is the basis for voltage. As electrons gather on the right ball, voltage increases until it overcomes the resistance of the gap between the two balls, at which point the spark is generated. The important things to remember are: unlike charges attract and like charges repel. This repulsion is the source of voltage in an electrical circuit. The second law states that the force of repulsion or attraction is inversely proportional to the square of the distance between the charges. For like charges, the closer the charges are together, the greater the force of repulsion. Finally, the Earth is called the ground. It is an infinite reservoir of electrons. Need some electrons? Go to ground. Need to get rid of electrons? Again, go to ground. This will end my presentation. Thank you for your kind attention.